Good morning, everybody. Today, our first speaker is Tim Laux from the University of Heidelberg, and he will talk about generic level set in mean curvature flow with and without obstacles. So please, Tim.
Good morning. Yeah, welcome to Mean Curvature Flow Day. um, yeah, nice to see you. Thanks for to the organizers. And Matteo is maybe coming late. Thank you for having me. It's a great pleasure to be in Pisa. There's actually a connection of this work to Pisa because Kaisuke and I met in this room the first time 8 years ago. So we haven't been working on this ever since, but so that was the first time we met, and we knew each other from paper, and kind of just last year we met in Japan for 3 weeks, and then he came to Regensburg back then when I was there, and that's where we kind of did this paper here. So I'm also going to talk about so this preprint came out today on the archive, so you can check your email, and then it's going to be somewhere, I think, at the bottom of the list, probably submitted yesterday evening. And so the little bit older work with Anton is something that started in Bonn. So there. To maybe to make some advertisement for the Bonn Junior Fellowship. This is a wonderful opportunity for young people. You should apply because you do have to teach a little bit, but you can teach whatever you want. So I taught on mean curvature flow, and then you have brilliant students there. Anton was one of them, and you can teach them the most advanced math that you know. So towards the end of the semester, I would tell them, "Now you know everything I know." Okay, so it's just a fantastic experience, and actually, this first part that I'm going to tell you about wouldn't have been possible without the lecture, I think. So because there I had to read kind of the papers of Evans and Sprague very thoroughly again, and then I realized, oh, there's something very simple. You're going to see it. It's not difficult to kind of make this jump, but then it was a very nice master's thesis for Anton. So instead, what we did with Kaisuke, this is maybe a little bit harder analysis, and but you will also see if you write it down the right way, then it's kind of it's good that you're standing on the shoulders of giants. Evans and Sprague did some beautiful work in the 90s that then you have to kind of be very careful how to extend it. So I hope towards the end of the talk, I can convince you that kind of you can extend the proof, and I can also convince you that it was that it was a surprise to us that it worked, because when you study the obstacle problem, this is not like a nice continuous perturbation, but it's a very hard constraint, pointwise constraint, and you have to be careful when you do this. So usually what you add is a kind of a singular forcing or potential. So it's not a compact perturbation. And then you have to be very careful. And the proof, towards the end, you will see kind of my version of Evans and Sprague's proof. But yeah, I told Teresa yesterday, this proof should be forbidden because it works so well. But in the end, you basically have something, there's 0 times infinity, but it's 0. So, okay, yeah, bear with me. So I hope we can get to this. And let me explain to you kind of what the setting is. So mean curvature flow is an evolution equation for, let's say you can think of nice and embedded surfaces, but they will cease to be embedded after some finite time. So I take maybe I'll draw the picture here. So I take a nice surface gamma of t that is the boundary of ut, of some open set ut. And I want this to evolve over time so that the normal velocity, so this is just the speed, how fast it's going out or in. When it grows, I say it's positive. So this is, let's say, ut. Then this is positive is equal to the negative mean curvature with the sign convention that something convex is positively curved, as we know it somehow from, I don't know, the early days, how we would define things. So here the velocity would be negative, here maybe positive. somewhere here, very small maybe, and 0. Okay, so this is the flow. And well, it has two nice properties. So the structure is the following. So you have a comparison principle. And you have a gradient flow structure. Oops. So those are two somewhat two very different worlds. But let me write down what this means. So this means if you have two mean curvature flows, one is contained in the other. So the boundary is moved by mean curvature flow. So let's say this is true initially. Then this is true for all times. For all later times. So kind of inclusion remains preserved. And kind of the gradient flow structure means that there's an energy, this is kind of in an energy landscape. So there's kind of some energy that you want to decrease, and there's a certain friction that you pay for moving. And it's very simple. It's just you take the area functional of gamma t. I know I'm preaching to the choir, and then you get VH. Let me write it like this. In particular, it's non-positive. And in fact, I think I learned this, Giovanni, if I'm not wrong, I think I learned it from something you wrote in the selected papers of De Giorgi, that he came up with the idea of minimizing movements, because Armgren gave a talk here, I don't know here, but kind of in Pisa, talking about the Armgren-Taylor-Wang scheme. And so kind of this is the history. It's really fascinating that kind of from this particular case of kind of there's a gradient flow, and then they did a minimizing movement scheme, grew this amazing general field of gradient flows with kind of, using minimizing movements and kind of defining things very generally. So yeah, has fascinated us for a long time. And there's a maybe very simple generalization that I want to show you is so with obstacle. So I'll just do the following. Maybe I put two disks here. Okay. Okay, so I'm already inconsistent with my notes with the colors. So it's one of the biggest challenges for me now to be consistent with the signs and with the colors. So let's see. So I'll put some obstacles here. So they don't have to be spheres, but I mean, I just put something nice here. And I would like to tell the flow it cannot penetrate those regions. So for reasons that will become clear later, I'll call them phi and psi, these sets. Let's say open sets with a nice and smooth boundary. These are just fixed, this fixed data like my initial condition. I fix this, and then I want to run this flow and see what happens. So you can also just put things on one side, and they don't have to be connected and so on. But you see already, here it cannot flow in. So it can't be true that it's just this equation. And on the other hand, you you would like the area to, so to still have this gradient flow structure, and there it's maybe pretty obvious. I mean, at least if you think about what gradient flow means, it's pretty clear that you can, in principle, incorporate any kind of constraints into a gradient flow. Because I mean, when you start from minimizing movements, you can just constrain to this, and then we can put constraints on things. So it's pretty clear what this means. And even if you think of this flow, I mean, there's just a there's maybe somehow a Lagrange multiplier that tells you cannot that you couldn't go in certain directions. So that will change the equation slightly. So here the velocity, so here the velocity was very negative, so it was shrinking. So it has to be, so here's equal to minus h. Then on this set, it's greater or equal to this. So this is So when you're on the boundary of the interior constraint, well, you can move faster than the negative mean curvature, but you can't, so faster out. So actually it's going to be 0 here, but this is going to be a good system if you write it like this. And the reverse inequality on that here. Okay, and then, so this is going to be V will be equal to, so kind of when you don't touch the constraints, of course, you solve the same equation, and otherwise you have these inequalities. And then you have, of course, the constraint that, yeah, okay, so phi, and you have psi complement, and kind of our ut has to be in between. Okay, so this is the constraint, and then these are the equations. So it's just like when you do, I don't know, Laplace problem with a constraint that you know maybe has been studied quite a lot. It's exactly the same here. So kind of you get, at the contact set, you get just an inequality, and otherwise you have the equality. So we have these two worlds, and I want to show you today how to go between them. Yeah. So yeah, let's see. Okay. So I'll first say a little bit more about what you do with the comparison principle and the gradient flow structure. Because you know they're true, you can build weak solutions based on this. So now comes the biggest challenge. I'm going to draw a picture that resembles this here. So I want to explain the kind of viscosity solution, and I want to do it with the level set formulation. So I want to draw graphs of functions now, so that this is just, those are just particular level sets of these functions. Okay. So maybe here. So, okay, I hope I can do it. So I'll show it here in one dimension less so that I can draw it. So maybe like this, maybe like this. And maybe it looks like this. So maybe here it takes off, touches here. Okay. Oh yeah, maybe to continue here. Okay, so think of this as being a slice of the graphs that I'm drawing. So kind of like a slice through here somehow. And you see kind of there's a function phi, there's a function psi, and there's a function u. They depend on x, and of course u also depends on t. And the functions are ordered. So I'll continue here with the comparison principle. So because of this, that these things stay ordered when you do a foliation, you will remain a foliation. So you can think of foliating everything with level sets of one function. So I can think of looking at a function for which each level set moves by mean curvature flow. And my question is, what is the equation for that function? So this is the classical computation that you do. Suppose everything is nice and smooth, and you take just the time derivative of this function. Well, you get dtu evaluated there plus, so let's say I take a curve x of t, like a trajectory that is always on the same level set. Then this here will be 0, because I'm always, let's say, on the 0 level set, or kind of this value is not changing. And then I get x dot gradient u at that point. And so you get, with this funny sign convention that we have, dtu is v gradient u. And then you can plug these in. Now you know, so let's say in mean curvature flow, I'll just write it down in that case. You have v equal to So minus divergence of the normal. I'm maximizing the number of of minuses here, so it's just a divergence of this here. And then you get just the standard level set equation. So with obstacles, kind of you have kind of just the inequalities and so on. Okay. On this side, um, I'm kind of I would like to know so, and maybe let's say so this equation, so dtu equal to divergence of this. Maybe best is to multiply this out, and then you see it's a degenerately elliptic operator on the right. But with viscosity solutions, you can touch from above and below and kind of give a weak notion of this. You know this, and so that is our weak solution concept here. That is due to Evans and Sprague and Chen, Giga, and Goto. And here on this side, you can also define weak solutions. So here you get viscosity solutions. Oh, let's say viscosity solution. This one is actually unique, the level set function there. And here, not even the concept is unique, what we want to do. And so there's a Brakke flow that Salvatore will talk about this afternoon, or this morning, actually. Sorry. So Brakke, then there's this local Sturzenhecker, so BV solution, let's say. There's kind of, so the circle closed at some point that we started thinking about kind of the optimal energy dissipation rate as De Giorgi then envisioned it in this general case, back also in back in the case of mean curvature flow. And so you can look at those, and all of those have something to do with the kind of writing down kind of things that that look like, I mean, so on the one hand, the area, the energy dissipation, and maybe on the other hand, you can do integration by parts to define things distributionally. So all of these concepts do this in this way. So let me maybe write down, yeah, yeah. Maybe I'll write down the Brakke kind of computation that you do this here, but localized with any test function phi positive. Then you get minus phi h squared. So. And you just put here the inequality. And Salvatore will show you how you do this correctly in the right sense. And maybe this is Brakke. And maybe I'll talk a little bit about this one here, where you say, maybe in more detail, because this is what I'm interested in here, is that you you define really the things that appear in the equation, basically the velocity. And basically you define the velocity and the mean curvature kind of by integration by parts. So for any test function zeta, I will say I want to check how what the distributional derivative of the characteristic function of u is. That should be zeta times v, let's say, over ds. So how the volume of this enclosed open set changes should be the normal velocity on the boundary. So that is one thing. And then the other thing is maybe for every test vector field x, you have okay. So this is when you do the standard mean curvature flow, and if you do put the constraints here, so the way how Keske and I did this now in this work is that we say, well, here the perturbations that I allow there. So think of this vector field x pushing your surface a little bit. Well, it should respect the obstacle. So I cannot push you into an obstacle. So x has the constraint. So the constraint that was on the surface, I want to put it on the test function. So I say, for all x such that, and then I just have an inequality. I have to get my signs right. It's great. Yeah. For all x such that, so I take here the exterior normal and here the exterior normal. So it should point in these directions. Wherever you can say this, so kind of where the surface touches this. Also on gamma t intersected with. And the same for psi. So kind of the original notion without the constraints here is due to Laux and Sturzenegger in this celebrated paper from '95. So we wrote down this version of it with the obstacles because there has been some work on the obstacle problem, especially the viscosity solution side. So the left side on this diagram is very well understood, but the right column is not so well understood. So there's basically, okay, so if I'm not mistaken, so Keske had two papers there, one alone and one with Nick, where they prove a version of Brakke's inequality. So actually exactly Brakke's inequality, but just for test functions that are kind of compactly supported far away from the obstacles. So kind of there's no extra information you get on the obstacles. And maybe for Brakke it's enough, but I'm always a little bit skeptical because Brakke flows can jump in time, kind of things can just disappear. So I'm afraid that you might jump over an obstacle and so on. So I wanted to have something on this gradient flow side where you kind of really see the obstacles and kind of have a better hope that this is actually a well-posed solution concept, the best posed you could hope for. So there's always going to be non-uniqueness, but maybe it's consistent with strong solutions and so on. And it should be consistent also with the with other weak solutions like the viscosity solution. Okay, so this is what this is about. So I want to not just say kind of strong solutions are such solutions. This is easy to see, and when you have this and you're sufficiently regular, you're a strong solution. But you would, I would like to combine. I would like to build a bridge between those two here. So from the viscosity solution to here. Okay. So yeah. So let me maybe make a few remarks. Also, it's maybe also a little bit about me, how I got to know this problem. So maybe some papers that. So maybe I think so. The first paper that I found was Almeida, Chambol, Novaga. So who used kind of this kind of minimizing movements approach, basically the Amund-Taylor-Wang scheme, but Antonon's version of it, which is a very smart way of implementing it. And then it's very nice to prove kind of that things are viscosity solutions and so on. There's maybe some other things, maybe some personal note. So I got to know this the first time. There was a fellow PhD student in Leipzig. Philip Lugaridge, he left academia. So he was just maybe 1 or 2 years above me. And so this is not a paper, but it's this PhD thesis, which is a very nice thesis if you want to read it. So he does the graph case. So you have your graph of a function, and then he wants to construct solutions using this Amund-Taylor-Wang scheme. So maybe I should say Amund-Taylor-Wang, Lucas and Sturzenegger scheme. So kind of this minimizing movement approach that inspired De Giorgi also. Now with a constraint, but he assumed they were graphs. So there's something remarkable that he could prove, is that you get strict convergence. So we've had some discussions about topologies here. So kind of the problem with constructing solutions in this sense here is that it's you're in this setting of functions of bounded variations or Kac-Schöpfli sets, and in order to pass to the limit in these things, you somehow so here this first variation is in terms of a varifold, and this thing up here is somehow in terms of a current. So there's two worlds, and they have to coincide, otherwise this setting doesn't make sense. And in Laux and Sturzenegger, this is an assumption where you assume that you have strict convergence. You know you converge weakly in BV, and it's just very hard, and kind of just in very special cases you can prove this. So like, for example, in the mean convex case, and in the smooth case, you can prove that the area converges. And this is exactly what Philip shows here in his PhD thesis, that also in the obstacle case, if you do the Amund-Taylor-Wang Lucas-Sturzenegger scheme, and you start with a graph, then you remain a graph, and there's no cancellation of area, and you have strict convergence. So this is something I think is very remarkable. It's maybe not. It's kind of clear when you look at the counterexamples why it's kind of the counterexamples that we envision that could be counterexamples, that it works here, but that you can find a proof that it does it. It's very nice. So this is a very nice thesis maybe to look at some point. Then so about the viscosity solutions, I said there's a lot known here. So there's a very old preprint by Mercier, and then some alternative way by Ishii, Kamata, and Koike. They prove existence of viscosity solutions. And then it's always unique, this thing. Maybe I tell you maybe two things about applications. So one application, as you infer from the name, is very theoretical. So Emanuele used this, I mean, not exactly the mean curvature flow with obstacles, but it's kind of exactly this time discretization. But kind of the idea is you run the flow for a given obstacle, and then you get some kind of hull of this obstacle, which he calls the mean convex hull. So you have to be careful how to define it so that you get this, but kind of you converge to this thing, and this is something that you can look at as an object. And then he used this to prove optimal regularity for the mean convex hull. How do you do this? I mean, he takes the limit t to infinity. So then these things should converge to this mean convex hull. So in 2D, it's very clear. So I just take the inner obstacle, the red one, and let's say this one is not convex. So yesterday night, I ran some simulations and have a little, it's like wrapping a gift, and then you have to guess what the gift is. So I don't want to show it here to not upset our technician. So I can show you maybe in the coffee break or so on my laptop. So it's a funny game that you need to guess what the obstacle was that you're wrapping. So let's say I start with some big sphere around it, then I let it flow. So here's my obstacle, and in 2D you're just going to converge to the convex hull, right? This one here. And I have a nice example for that maybe fits here, but I'll show you later maybe if you want to, where you need to guess then what was phi, kind of that I wrapped in my gift wrapping paper. Sorry? Oh yes, of course. That's why it's a game. No. It's kind of. I'll show you my simulation, and then I hope somebody can guess what it is. Okay, yeah, exactly. It can be many things. So in here it's completely ill-defined what it is, but that's why it's a nice game. So so what you see directly here is that the optimal regularity that you can hope for this white curve is C11, and that's what he proves. Okay, using this this kind of flow. So why I then in the end actually got interested in this was just last year. There was a beautiful conference in Niseko organized by Yoshikatsu Giga and a whole kind of group of people around him. So there, Kaisuke gave a talk on his work and his work with so maybe Nick with Nick that you get a Brakke type flow. So what they do is they start with Alan Kahn. So if you know Kaisuke, it's maybe not surprising that he started with Alan Kahn. You add some singular forcing, kind of that is kind of depending on your epsilon parameter, it kind of degenerates as epsilon goes to 0, and that kind of enforces the constraint in the limit. But as I said, kind of they know nothing what happens when you have the contact. So there's your test function is not allowed to live there. Yeah. And then maybe, so at this same conference, there was a physicist, Olivier Pierre-Louis. So the reference is Martin Kai and Pierre-Louis. So who try to so they actually do it's kind of interesting. So they do kind of a so they want to understand the following problem. So you have a substrate and on top you have a layer of graphene. So you put this on top. So he's a theoretical physicist, but that's kind of so that's kind of there's two layers. There's an experiment that he actually compares his theory to, and now we're a little bit more theoretical, maybe even. So there's a layer of graphene on a substrate, and now you put little nanoparticles below. For some reason, you do this. Okay, so this is what the experimentalists did, and they wanted to see when does this sheet lift up actually. So we'll want to have contact, and kind of how many of these little balls do you need so that it actually lifts up. And this is what they call an avalanche. Kind of if you have a certain number of these little balls, then it's going to kind of completely take off. Before that, not. And kind of there's kind of it's kind of more like usually phrased in kind of probabilistic terms, and then you sample these points where they are, and kind of see, you want to see kind of what's the threshold at which kind of you will have this that it takes off. And here, kind of his model for this is exactly, so it's 2D. You look at it from top, and you start kind of where it's kind of not touching, and let's say this is a little area around each ball, kind of that's kind of not touching, and then you do exactly this this flow. And what he gets is kind of a so he uses this as kind of, he wants to do numerics for lots and lots of these little balls, so that then you can kind of actually say something useful, because you need a large domain and lots of these balls. So it's a very interesting computational question how to do this. And they can't actually, so they have to modify the system even more so that they can actually do the computation. And I was interested, could you do computation there? So that's maybe the long-term goal, to maybe understand these kind of phenomena. And of course, I mean, it's his theoretical physics toy model for this actual experiment that I showed you. But I mean, just to show you that there's interesting recent applications also of this kinds of flows. Maybe the more classical ones are, we think of grain boundaries, and there are maybe dislocations that they can't get through, or so there's some kind of some impurities or so, which I'm not sure is maybe also good application. Okay. Yeah. So here's the theorem. So this is this, I mean, from today, is that almost every level set of the viscosity solution is a distributional solution. Okay, let's say a BV solution. In the sense that I wrote down here. Kind of the mean curvature flow with obstacle. So kind of these, I mean, and in particular, we prove existence for kind of generic obstacles of these kinds of distributional solutions. So this is based on two things. Kind of there's this book of this series of papers by Evans and Sprague, and I would say my favorite one is number 4. Encourage you to read this one. So they do the following. Kind of this equation looks bad because kind of there's the modulus here. Kind of you see kind of it's there, you see immediately that it's kind of degenerate. You can also multiply it out, and you see always kind of the problem is that that I have the modulus here. So in some sense, I would. So I don't want to divide by 0, or kind of then this is kind of not exactly defined. But on the other hand, you can also see that when you multiply this out, kind of the product rule, you will see that kind of there's a matrix that has 1, 0 eigenvector, and that one is because this is a unit vector and it's not short. So I would like to make this a short vector. So what they say is, look at this here. So for epsilon positive, you look at this equation here. So everywhere where I had the modulus, I put the modulus of the vector gradient u and epsilon. So this is, when epsilon is equal to 1, this is exactly the mean curvature flow of a graph in 1 dimension higher. Okay, so this is, and now they made this amazing observation that this is a great way of, I mean, so there's going to be existence and regularity, and this is a beautiful equation. It's just a nice parabolic equation, and you can run this. The question is, can you take epsilon to 0, and what does this have to do with the actual viscosity solution, or kind of the mean curvature flow in one dimension less? And kind of you're squeezing this kind of like this, and so then it becomes kind of vertical and becomes basically reduces to this one thing. So this is kind of the idea. Beautiful idea, and this is the kind of the most beautiful approximation maybe of mean curvature flow, I guess. I think right now. So so it also has, of course, because it's the mean curvature flow of a graph, it's also a gradient flow where the energy is just well, oops, the area of the graph. Okay. So what do we do? What I put there is a potential. So you have this mean curvature term, and then I put here, okay, sorry about this. So I put here a potential. So I do a kind of this graph mean curvature flow in a potential, and this potential is going to be such that I want to, so this is v epsilon prime, so that the energy is this plus v epsilon of u. And this potential wants me to preserve the two obstacles, or kind of respect the two obstacles. So kind of what I take is, so v epsilon of u is going to be something 1 over epsilon, so that it penalizes this. And then I take my phi minus u positive to some power. We take the power 4 for some technical reasons. So that is nice and smooth. Let's take power 4 here. So take the positive part here. So it's kind of, whenever the constraint is violated, one of these is going to be positive, and then kind of take epsilon. Okay. And there's, you can do now some basic things like gamma convergence of this energy. Kind of the actual topology that you should look at is uniform convergence, because this is what you get from this from the construction. So these things always converge uniformly, as you know from the kind of viscosity solutions. Is always like that. So in the uniform topology, this converges to just, let's say, E of u of the which is let's say this if the constraint is satisfied and plus infinity otherwise. So this is really a kind of, in Bonn it's a bachelor's exercise. I didn't study in Bonn, so for me it would have been hard, but I mean the students there are just really fantastic. So and you get, of course, energy dissipation. And let me write this maybe in this way. So I call delta E epsilon kind of the first variation that you might want to define. So for the solution of this thing, I have this energy dissipation, and so you get that this thing here is in L2 with respect to this measure. Okay, nothing interesting happening here. Now come Evans and Sprague. They say, well, there's a really funny exercise, funny estimate that you can do. It's this. So on the same quantity, you can prove this. So let's say xt. So uniform in time, L1 in space, and there's no area factor. I mean, I think, Okay, so maybe in words, Craig told me this is strange. Maybe they even call it strange. I call it strange. This is a strange estimate because it's not kind of, it doesn't reflect kind of this level set by level set. Kind of the level sets are talking to each other. So it's because you're making this particular approximation here. This is the kind of estimate that you want, and this is the proof that is kind of that should be forbidden because it's just beautiful. I'll show you in a moment. Maybe I'll say just a couple of words why I'm mentioning Anton, who's finishing his PhD and now moving to Pittsburgh. What we observed there was that you can. So what you do once you have this estimate, you can do you know, this is the first variation of this thing, and let's say without the obstacles, this is the divergence of this guy here, and then you write down the energy and do a compensated compactness argument. You get measure times a function that converges uniformly. You can carry this out. Then you get strict convergence, and you can kind of everything works out well. So in the last 3 minutes, I'm aware of this. I want to kind of tell you a little bit how you get this, which Anton and I didn't have to worry about because it was done by Evans and Sprague. Now you have to look at this proof, which is really amusing because it's just it works so well. But you have to be very careful because this perturbation that you do is you know, not compact. You have this 1 over epsilon here, of course. Okay, so you have to do it the right way, and I think kind of got lucky that it exactly worked out. So how you get then from how you get this equation here? Maybe just one last comment on this is you for the u epsilon. This is a nice and smooth function. You can get all these kinds of equations for that kind of that look like that somehow, and then you have to take epsilon to 0. You have to see that the things pass to the limit. So you write down those equations. With this estimate, you can pass to the limit, and then you get kind of a version of this distributional equation, but for the level set function. So everything is integrated over the level sets, and this is kind of what Anton and I did, is that we realized that not only can you do co-area formula for all these surface area terms, but you can just do the layer cake formula for this term here, and then kind of things just fall into place, and that you kind of can disintegrate the level set variable. Okay, so back to this new work with Keisuke. So I want to tell you why this here is true. So how to prove this? So the idea is that so ddt of this functional is less or equal to 0. Okay, so how do you compute this? Well, there's another modulus here which I don't like. So you take some nice and convex function that looks like the modulus. So you take a convex function that eta of 0 is 0. So should look like this. So here we had the modulus. So it's a little bit below the modulus because it has to be nice and smooth down there, but kind of you can make it uniformly close. If I kind of tell you, I'm going to later take a small parameter there. Okay. 1 minute. Okay. So you take eta of this thing. So okay, of u epsilon and so on. Okay. So I evaluate this at a later time. So dx, and I evaluate this at a later time. So of course I write this as the derivative of this, kind of with fundamental theorem of calculus, and I get this thing at the initial time, plus a term that is kind of that I have to compute. I'm not going to do the computation, but trust me, if you just use the convexity and you do integration by parts as you please, you get something like this. Okay, so there's 3 terms in this last integral that is left. So there's the second derivative of this eta, which is degenerating, right? I mean, this is exactly the thing that blows up. I have the gradient of this function, and I have this function. Okay, so this, just trust me, you can do this computation. It's not so bad. And the c epsilon goes through the ceiling, it's like 1 over epsilon, and then you take derivatives of the u epsilon that you're not allowed to take. So it's kind of all this is, you have no control on c epsilon. So now I take this scale here, let's say alpha. So eta double prime, so the support of this should be in minus alpha alpha and eta double prime. So of course less or equal to 0, but okay, greater or equal to 0 and less than alpha. Okay, so you can do this because it just has to go up to it's because it doesn't have to go up to 1, but just to alpha. It kind of has to go like the, yeah, so this is important. Okay. 1 over alpha, sorry. I mean, otherwise it wouldn't be so difficult. Yeah, but I mean, it's not 1 over alpha squared because you just have to go up to alpha. So let's do the estimate. So this is, I get the 1 over alpha, which I don't like, but then I just have to integrate there where this delta E epsilon is less or equal to alpha. And I'm integrating whatever I had here. Okay. And Sergio already saw what happens, right? So this is less than alpha, so this kills this guy, and then, okay. So you get, so integrate this over the set where this thing is small, less than alpha. Well, now you can take alpha to 0. So alpha from up to 0. So you get integrate over the set where this thing is 0, the gradient of this thing. Oh, that's 0. Okay. So there's several zeros at infinity. Maybe somehow kind of this that is 0 is just amazing, and it's the prefactor of the c epsilon that goes through the roof. So there was no wiggle room, and it works out. So kudos to Evans and Sprague, and we were very happy when we saw that that you can do this. I mean, so I wrote it down in the right way, that you take the first variation of the energy and not the mean curvature. So if you try with the mean curvature, we tried this too. I have to admit, it doesn't work. Because kind of, I mean, things don't compensate. And here, it's, of course, this is the right thing, the second thing you try. And it just works out, but you have to be very careful. There's two things. Of course, this eta is has to be convex. And although this problem is very non-convex, in some sense, you convexify it when you go to the level set formulation. And the potential that we put there is also convex. And then everything works out. Okay, so this is maybe the ideas, and yeah, sorry for going over time, Anita. So yeah, thanks for your attention.
The team for the nice talk. So any question? Oh, okay. Where do we start? There.
If you replace the mean curvature flow, but by the Laplacian flow, it is well known that the obstacles can also be thin which means one-dimensional than the in your picture, the red circle could be a segment. Is this still possible for the mean curvature flow?
Excellent question. So as I said, this prepared we got out today. Excellent question. I mean, I think this is hard. I mean, even in the Laplacian case or heat flow case, it's not easy to go from a thick obstacle to a thin obstacle. Would be nice to see. I don't know. So here, we're not only assuming that these obstacles are, fat, but kind of they are somehow also a little bit regular. So I don't know. But it's an excellent question. Yeah. So you could maybe do another limit after. So make the I don't know. Just improvising now. Maybe we could first do this and then make the obstacle thin. I don't know. Yeah. So would have to look into it. It's a good question. It definitely makes sense for the obstacle, and maybe in biological applications, it's actually interesting to do that. So, yeah, definitely. I mean, kind of if you. Yeah. No, of course, mathematically it makes sense, but there's kind of applications in biology where you have actin filaments inside a cell, and kind of they are kind of, imagine them as sticks. kind of segments, and there's lots of them in there, and kind of the cell membrane can shrink and so on, and kind of it cannot penetrate those. So it's definitely a really good model, but I have no idea right now. Yeah, thanks.
I have a couple of questions. The first one is I didn't really understand the model when you said that the velocity has to be greater or equal or less or equal than minus h, depending on which obstacle you are close to. Because in a way, if when you touch the obstacle, I would say that the velocity has to be tangential, because and then it's not a scalar. And then what do you mean by greater or equal, less or equal?
Okay. Thanks for the question. I mean, next time we meet each other at a conference, you can stop me and just. I should have done a better job. Sorry. So v is for me just the normal velocity. So it's a geometric problem. So I can, by reparametrizing everything, you don't have to worry about the tangential velocity. So this, I completely agree. So if you think, let's say, this bold v is the actual velocity field that you take. The only thing I have to take is this dotted with the normal. This is the only thing I wrote that was on the board. So I never, in this computation up there, you see it's x dot, the gradient of u. Gradient is kind of in the normal direction to the level set. So the other thing doesn't show up anywhere. So kind of, exactly, you're completely right. So here the velocity of this white surface could be in tangential direction. But when I look at the surface as a geometric object, it doesn't change if it's, you take a circle and rotate it, it's not changing, right? So it's kind of these tangential velocities don't play a role. And I kind of completely ignored them, and thanks for bringing this up. Yeah. I'm saying it could go into this direction, but there's no reason it should. There's just the inequality, and that's enough, because maybe I should say one more thing. So here also you have an energy dissipation relation that says that kind of energy is going down. So there's no way that you want to kind of detach again there. Okay. Yeah.
Okay. Thank you. And then I have another question. So what do you expect the solution to be in that situation as the time goes to infinity?
Okay. Yeah. So my next drawing exercise. So I think it's going to look like this. Oh no, wait. Sorry. No, it's going to be this. I have another example. Actually, I didn't copy.
So you just avoid the obstacle, the psi obstacle, and then you shrink.
Let's do something nicer. So that's something that I actually had in mind when I started drawing. So let's say phi is the union of those two. Then it's going to look a little bit more interesting. Then I actually have to go here. Then I have to go here, and I have to go here. Okay, so it's going to be nice and straight line segments until they reach there, and kind of here, kind of as t goes to infinity, this is exactly what Emanuele proved for the time discretization of this. But kind of he proved that kind of you converge to what he calls the mean convex hull in this case. So I also have this one here that pushes in, but kind of in 2D it's just these without this, it would be the convex hull of the union of the red things. And so it's red lines, and then here it's exactly following the obstacle.
Okay. And can't the solution break into pieces when touching the obstacle just to shrink faster?
Yeah. That could. So in 2D it's not happening, right? In 3D, that's why I said you have to be careful when you define the mean convex hull, because you have to define it in the right way. In 2D, and also in 3D, this could be a thin channel, and it could pinch off. So in 2D, this is not happening. In 3D, it could happen. And then you could have kind of two circles around each of them, right? Yep.
Okay, thank you.
Okay, thanks.
Okay, I think we have still time for one short question. And I see one here, two here, two there. I don't know who wants. Okay, Teresa, you go.
Okay, so I studied in Bonn, and I learned most of my gamma convergence from Sergio.
You did do this in your bachelor's. Okay.
I did not do this in my bachelor's.
Yeah, sorry.
How do you get compactness in C0?
Okay. So
the rest is okay.
Okay. Okay. The question is kind of under which conditions you put there. So usually you so, so usually you're in this space of Lipschitz functions. And so kind of in our application where we kind of have the flow, kind of anyways, the initial conditions are continuous. It's the level set function, right? So this one is continuous. It's actually maybe even nice and smooth. And then things stay continuous. Actually, if you're Lipschitz, you will remain Lipschitz. And so kind of you kind of get these bounds, then kind of you get this automatically. So how you get this for a general minimizing sequence? Let's see. um, so you got to be bounded. So Teresa, okay, bear with me. So you got to be bounded. Okay. Yeah, yeah. So kind of the application I have in mind, I do this for my for the flow, but kind of if you don't provoke jumps by taking some kind of irregular boundary conditions, then you will not have them. So that's kind of the obstacles. Let's say they are Lipschitz, the functions, and then you will be Lipschitz. Okay. Good point. Yeah.
Okay, our next speaker is Daniele de Gennaro from Bocconi University in Milan, and he will talk about elementary discrete diffusion, redistancing schemes for the mean curvature flow. Please.
Thanks, Alicia. So, thanks a lot for the invitation. I must say it's a real pleasure to be here today. And I must say also that it's a really nice conference you put together, so good job. So in today's talk, I would like to present some results they obtained recently in collaboration with my two PhD advisors, Antonin Chambrol from Paris Dauphine and Massimiliano Morini from Parma, concerning these essentially, so you can sell it saying that it's we are showing the convergence of numerical schemes. Actually, you are doing a discrete to continuum limit in the classical way. And before I start, I want to thank Tim also because he already did the introduction, so I like have 10 minutes spare. So we'll go. I hope to go quite slowly. So so again the setting will be the mean curvature flow as okay. So it's the mean curvature flow morning. So it's that's the topic. But I want to unfortunately say that I will use another notion of weak solutions. So just to to present it briefly. So okay, I recall you that the evolution equation is this one. I won't say what is it, but what I wanted to say is that if you remember what Tim essentially just said, where you are using the comparison principle, you can embed this evolution of sets into the evolution of functions, right? So essentially you have now a function u, which depends on point in time, and when essentially you're looking at a level set, say u less or equal than 0, you get another set which is in turn evolves by mean curvature. Okay, so okay, then you write down the evolution equation. Turns out it's something related to the degenerate parabolic equation, etc., etc. So what I want to write down is that if you remember, the evolution equation was so the divergence of grad u over modulus grad u. Probably there should be something like modulus grad u here. So just a small observation, imagine that your function u is a distance function, okay? What's the main property of the distance function? The modulus of the gradient is 1. So if you erase here and you write down d instead of u, you get a nicer operator, right? You get Laplacian. So that's, of course, it doesn't work, but that's why essentially there is this really nice paper by Sonner, which rephrases everything essentially that has been done for viscosity solutions in terms of distance functions. Indeed, so the idea is the following. You can give a definition which says that a flow, so E for me will be a space-time tube, so in Rn times, let's say 0 capital T, is a distance, so super solution to the mean curvature flow if, so they tell me that the blackboard is quite heavy. So if the distance, so d is the sign distance function to the set E, so to write it down properly, d time t is the sign distance function to the set, to the time slice et. Okay, so the sign distance function, the distance positive outside, negative inside. So if the function d satisfies so dtd bigger or equal than delta d in the region where it's positive. So of course I draw a line and then again I went out, but so in Sonner's paper, he starts defining super solutions and then of course sub-solutions, which I will call distance solutions, or in general weak solutions during the talk. Looking at the sign distance function and saying that, okay, I'm a super solution if I'm going faster than what I expect, at least when I'm positive. So meaning outside of the right evolving set, if you want, I'm going faster. And of course, sub-solutions, I'm requiring the other inequality in the region, of course, where I am not positive, okay? Okay, so that's of course a differential inequality. In which sense do I need to satisfy this? And in Sonner's paper, he requires that the inequality is satisfied in the viscosity sense. Okay, so essentially it's the same framework of viscosity solutions, but now rephrased in terms of distance functions if you want. Okay, so just for today, I want to recall this other paper, which is by Chambol, Morini, and Ponsiglione. I don't remember the year. It's on CPAM if you want. Where the idea they had is the following. So, okay, there is this really nice theory by Sonner, which essentially works as soon as you have, okay, so it works for the Laplacian, it works if you have some smooth operator, essentially. So even in the anisotropic mean curvature flow, when the anisotropy is smooth enough. In that paper, they were more interested in some singular operator. So in that is the crystalline mean curvature flow. In that sense, the viscosity machinery breaks down. So the simple idea they had is that, okay, assume that we want to do the same definition and try to replace the same theory by a new one where we require the same thing to hold in the distributional sense. So I don't know where to write it. Let's say dtd bigger or equal delta d in the positive in d prime. Okay? So the main idea of the paper is this one, and of course you have many technical details. So what can you do with this kind of solutions theorem? So you can show that, so given an initial datum which is simply a closed set, then you can produce this kind of solutions. So and then there exists sub and super solution, which are unique, let's say, unique up to fattening. I will explain what I mean. And moreover, you can show, so if they are unique, I mean that the sub-solution coincides with the super solution, so you have a solution that is a flow where the distance satisfies both inequalities, one outside, one inside. And moreover, you can see that E, so if the smooth in curvature flow from E naught exist, then for some time, then it coincides with E. Sorry, yeah. Okay, so E, I'm denoting the distance solutions. Okay, so they can show, yep. So they can show existence of sub and super solution, uniqueness, up to fattening. What does it mean? Okay, so for the mean curvature flow, you sometimes have bad behaviors. So for instance, consider the following example in dimension 2. So this is your initial datum. You want to let it evolve by the mean curvature. So actually, the flow doesn't know what to do in the singularity. So you have two possible behavior. Either you desingularize in this way, so you disjoin the two sets and that let it evolve. Or, for instance, you can do this. You can join them and then let it evolve this way. So as you can see, more or less, this is contained in this other solution. Okay, so when fattening happens, it means essentially that the evolution from this set. So the solution is not unique, but there are essentially a super solution which morally is behaved like this. I hope you can see. Okay, and there is a sub-solution which essentially is inside, if you want. Okay, so the fattening phenomenon happens when your evolving distance function has as zero level set. So the boundary, if you want, of the region where you are satisfying one differential inequality and the boundary of the complement of the one where you are satisfying the other has positive measure. Because if fattening happens, so whenever you have this kind of non-uniqueness, you will see that this level set will have a positive measure, okay? And this is the fattening phenomenon. So generically it doesn't happen, it may happen. So essentially the theory is quite well developed, but in every statement you see, you will see this caveat, assuming fattening does not happen. Okay, so what was our goal? So to present it briefly, the idea is the following. So we have this nice plethora of weak solutions, but we want to make some numerics essentially, right? So we want to see what's happening for the mean curvature flow, maybe in ninth dimension, maybe past singularity, etc., etc. So what do we do? Essentially, you try to devise some approximation schemes. For instance, the minimizing movement one that was presented by Tim. But computationally, you need to do it on a computer, right? So essentially, you will need to have a fully discrete way of approximating this this evolution. With fully discrete, I mean space, time, which sounds weird, discrete approximation scheme for the mean curvature flow. Okay, so for instance, you want to do the minimizing movement scheme, you need to discretize also the space, because of course you need to work with a computer, so you need to discretize the sets. Okay, so for instance, so like for viscosity solutions, you are working with a PDE, so you can discretize everything and use classical numerical tricks. What we wanted to do actually was trying to look for something quite simple. So there is this very well-known way of approximating the mean curvature flow, which is called the MBO scheme, so a convolution thresholding scheme, which is based on the heat equation, and it's fast and also quite accurate. But actually, we saw while we were working on this project that essentially we could go away from the simple algorithm and then consider more general algorithm, as I will try to explain later. But let me just introduce a little bit of and show. So the goal was to show the convergence of these schemes as, let's say, the discretizations goes to 0. Okay, so that's the main idea. At first, we started with some kind of scheme like the MBO scheme, etc., etc. So just to cite a little bit of literature, there is this. Okay, maybe I can write it down. So there is this paper by Ezidoglu, Root, and Tsai, where they are studying the convergence from the discrete to the continuum of the MBO scheme. And what has been done in the literature and what's already done, well, I mean, usually done, is you say the following. So assume that you have a space discretization parameter epsilon and a time discretization parameter h. So after it will be clearer, but you can think of it like maybe you want to do a minimizing movement scheme, you discretize the space, you consider a lattice of spacing epsilon, but you also discretize the time, the evolution, and you discretize by a step h. So what they saying is that if epsilon is way smaller than h, morally, so if I let epsilon to 0 and then I let h to 0, then I recover viscosity solution. So I will write the MBO scheme, which I will not discuss for a moment. Scheme is consistent. Okay. There are some other, okay, maybe you can also consider variants of that, but there are other results. So there is this nice work by Misitas, Yip, when we're doing the same analysis in 2 dimensions, and they can show essentially the same thing with a slightly, okay, so this was morally. So they sent essentially epsilon to 0, then h to 0 in their algorithm. So they had a fully discrete approximation sequence. They sent epsilon to 0 and then h to 0 in this sequence. So it's a little bit different. So here they are saying that morally the result is that if epsilon is small of h, then the same scheme is consistent. But what they show is quite is more interesting, because if if epsilon is of the same order of bigger than h, then we have pinning. So pinning in the context of discrete approximations means that you have your initial datum, you run your algorithm, but somehow you devices your algorithm in a not in the proper way, and so your initial datum does not move, even if you know that you should move, because essentially, of course, you expect it to move. But essentially, so this is saying that the kind of schemes that were present in the literature before, I mean, I won't say they're not okay, but I just need to say that they needed some kind of fine analysis on the convergence. But also I would like to mention also this recent paper by Laux, by Tim and Lelmi, where they're working in a different setting, where you have now, so the space discretization comes from essentially sampling a distribution that you have, and on the graph that you build from the sampling, you can do some kind of approximations. But and so also here they have a nice analysis essentially on this kind of what kind of relation do you need between epsilon and h, and so let's say in their context is much more difficult. So this is from the mathematical, I mean, proper math, let's say. But I want to lastly cite this paper, this really interesting paper by Breton, Denis, Masnou et Terry. Masnou, Terry, which, for for what I know, is the first time that finally neural network have arrived for the mean curvature flow. So if you, as me, are not excited by that, what they do essentially is they train a neural network to approximate the mean curvature flow. And the crazy thing for me is that the sample is just made by 100 pictures of balls, just balls. Okay, you explicitly know the mean curvature flow for balls. Essentially, it's an ODE for the radius. You produce 100 pictures for that. You know how to do it. It's super easy. You put that on a computer, and then what can he do? What can he do? Essentially, he can simulate anything. He can simulate the mean curvature flow past singularities. So even if you are only train them on balls, they know how to desingularize the flow. They can do partitions and slightly changing the architecture, but not much, and also keeping the same training set. They can also do non-oriented evolution. Which helps when you are trying to provide the simulation for Steiner trees, for the Plateau problem, for the Steiner problem, etc. Okay? Amazing, right? So our humble goal, so Anton's goal essentially was, let's try to understand what's going on here. Because if you read, I have to be careful the paper, they are doing the following thing. So they are building, I won't write it down because I don't want to write wrong thing, but what they are doing essentially is the architecture of this neural network is based on two different steps, if you want. The first one is learning something which resembles the Allen-Kahn step. So they are doing a step of the Allen-Kahn. But then, morally, really morally, because you want to work with distance functions, let's say, if you do just a step, okay, so think that you want to show something about the distance functions. So you do a step of the Allen-Kahn. The Allen-Kahn essentially is a diffusion. So you diffuse a little bit your distance function, which now is no more a distance function. So what do? You essentially use a redistancing. So that is, you modify your new function so that it becomes a distance function, right? So the second step in this neural network, morally, is learning how to redistance the function in a really clever but not so obvious way. So, okay, so the title, if you want, comes essentially from this kind of algorithms. So we wanted to show how far can we go in studying a general diffusion scheme, which is coupled with a redistancing scheme, and try to show how this converges towards distance solutions. Okay. So. So what's the setting that we considered? So we consider, as before, two parameter epsilon h. Okay, so at first just epsilon, positive. And we work on the rescaled regular grid, epsilon zn. Okay, so at first we started with the easy case, a regular grid, rescaled it, and then try to send it to 0. So just to fix a little bit of notation, if you are consider a function u on the grid, usually I write ui to denote the evaluation. And so on the grid, there are many discrete versions of differential operators. The one that I will care the most today is the discrete Laplacian. Okay, so this one is simply defined as a weighted average of the second order finite differences. So you take u, so let's say minus 2 ui, and then you add ui plus epsilon ek, and then ui minus epsilon ek. Okay, so essentially it's a convolution, a local convolution, which has this weights and 0 otherwise. Okay, so you can show that this thing, this operator converges towards the continuous Laplacian. So the scheme that at first we had in mind is this really simple explicit Euler scheme. Explicit Euler. So the idea that, no, I erased it. Ah. Oops, I'm really sorry. I mean, this is a simple equation, right? Okay, so imagine for a moment you want to discretize this kind of equation. Forget for a minute that you want to work with distance function. Easiest possible numerical scheme, Euler explicit. So what you want to do, you take your initial datum U naught, which for simplicity, you take the same distance function from the initial datum you had, restricted to the grid. Then you iterate, putting UK plus 1 being equal to UK plus a time discretization parameter H, delta epsilon UK. Okay? So that is the fully the elementary part. As I was so here you introduce a time discretization parameter. You can write this down as a convolution kernel applying to UK, where this kappa you can find it explicitly, but if you add to this what is UK, then you multiply here by an H, you get what's the point. So as I was saying, this thing, since we are morally approximated the heat equation, will diffuse the distance function. So if this was a distance function, this one could not, maybe is not a distance function. So what we do is that we use a redistancing of this. So this is the so-called redistancing operator. And now I would like to sketch, to present what is the redistancing that we ended up using. So actually, so redistancing operator is the. So actually, this operator had been already introduced in a previous work with the two my two advisors, Chambol, Morini. When we were working in the crystalline case, but then we essentially the definition can be used in a much more general setting. So I first write down the definition, and then I try to explain. So consider U a one Lipschitz function. No, we are thinking about distance function, so it's fine. So a discrete one Lipschitz function, right? So the ui minus uj less or equal than distance. And what you define is in two-step. So you first define this. This one should be the positive part essentially of the distance, which evaluated a point you define as the infimum, right? Yes. J where u is negative of uj inf, so it's a plus like that. Oh yes. Then SD of u, which is the full redistancing operator, is defined starting from the one above. So sup j, the region where u is positive, of d of u j minus modulus of I minus j. Okay, so essentially you define by inf convolution some kind of operators. So at first glance, this definition doesn't say much, but it turns out that you can prove the following property. So at first, if u is one Lipschitz, you can show that SDU is again one Lipschitz. And then you can show the following characterization. So du is the, I don't remember, largest, smallest, largest. One Lipschitz function, which lies below u in the region where u is negative, right? Yes. And then as d of u is the smallest, one ellipsis so that is above d of u when u is non-negative. So actually, what we did essentially was starting from this definition, go back to the characterization with the infinite subconvolutions actually. So why is it a little bit more handy as definition? Because now assume that you have so your grid here, and you have your function u here. Morally, you can see how this redistancing operator works. Okay, so you would expect essentially the redistancing to be something which is approximating the distance function from the zero level set of the function u, but u. So in this picture, u is the u here is a continuous function, so you know how to do it. But assume that your for your u, you only have the values on the grid, right? So for instance, u essentially is a, is a list of points on the grid, which may also not even be equal to 0. And you want to build something which resembles the same distance function from the 0 sublevel set, okay? So you need morally to interpolate somehow to catch the true 0 level set. So you can do this in many ways. Of course, you can just say, okay, I don't really care. I take the set where so let's say, for instance, u smaller than 0. I take this, and then maybe I add some squares so they come back to the continuum. I take the distance function, I restrict it to grids, etc. The issue is that this construction, which was the one considered in the previous literature, creates too many errors. And you will see later on why. So the construction here instead does the following. So you take u, and you want to build first du, which is the largest one Lipschitz, which is below u. So actually you keep u, so you keep these values of u, and then essentially from this, you shoot with the maximal one Lipschitz function you can use. Okay, so for instance, you will grow a little bit more. And then from this, the u essentially keeps the same values, but then shoots back. So it grows, it's a little bit less than u when it was negative. So as you can see, here somehow we are a little bit interpolating. Okay, so that was the idea. But what can we prove, and that's I think the interesting part is that you will see in the convergence proof that this fact is super helpful. You can show that as du is above u when it's positive, and it's below u when it's negative. And okay. So just to let you understand where are we going, a small spoiler. So take this. Assume now that you want to be a super solution. You want to look for a super solution. So you start looking at the region where D is positive. Where D is positive morally means that UK is positive. Or let's say UK plus 1 is positive. So essentially, since the positivity of this is equal to the positivity of the redistancing, you are in the first region. So the argument, so this is bigger than the argument. Okay, done. And of course, in the other region, it's the same. Okay. Of course, there is something missing here. So you have this, and of course, so if u was equal to the restriction to the grid of some one Lipschitz function v with v one Lipschitz, then essentially you have that the as the u is close to the true sine distance function from the 0 sublevel set on the grid. Okay, so I want to stress this fact. So here we are not making much, okay? So here we are saying, okay, I am approximating over the epsilon, an approximation over the epsilon. The interesting thing, as I sketched there, is that when you want to look for the limiting equation, these schemes, so this redistancing, does not produce any error term, as you can see. On the other hand, this is saying that it's approximating in the right way. If you had used something which already already created some approximation errors here, that means in these two inequalities here, you would have had a new error term appearing there in the equation. So when you pass to a limit, essentially this gives you a new error term, which appears here if you didn't cancel it out when you're passing to the limit. So you needed some kind of assumptions on epsilon and h to cancel it out. Okay, so before stating the main result, I want to introduce the generalized kernel. Because essentially, so that was the main idea, but you can see that there, at least for the equation, you don't need the expression of the explicit kernel. I mean, that works for any kernel kappa. So what we ended up defining is this kind of generalized kernels, which then, we try to interpret in different numerical schemes that were already present in the literature. So we assume that the kernels are okay, they are defined on the grid. They are symmetric, positive, not negative. They sum to 1. And this is the funny part, if you want. They have finite second moment. Not only that, but what we define is essentially this as h of epsilon. So if you remember at the start, if you remember for that, before we had an epsilon, an h to work with, which was the time discretization parameter. What we devise is that you just have a kernel here, which already encodes somehow the time discretization parameter, okay? Which pops out when you're doing the second moment. Indeed, for instance, if you take the Euler explicit scheme, you call the h tau, for instance, and you compute the second moment, you see that the second moment is equal exactly to tau, okay? So then this definition makes sense. And what we require that simply this goes to 0 as epsilon goes to 0. And 4, so that's okay, so this is only some structural assumptions. And concerning convergence, we require that kappa epsilon is converging to the Laplacian in a weak sense. Namely that if you take the Fourier transform, you take out 1 and divide by h, this is converging to the symbol of the Laplacian pointwise. So this is the discrete Fourier transform defined on a, so you can interpret as the coefficient of the Fourier transform. Okay, so this of course is, okay, so the main result that we have is the following. So assume that kappa epsilon are as above, and h is smaller or equal than epsilon, is bigger or equal than epsilon squared. Okay, so that's the only, if you want, constraint that we have. Then the algorithm, which I just erased. So the algorithm, which is defined as So UK plus, sorry, UK plus 1 is equal to SD of kappa epsilon convolution UK. Produces functions, which I call d epsilon of t, which are simply defined as u. So here, of course, u depends on epsilon. U epsilon evaluated at t over h. Such that, so we have that the epsilon converges as epsilon goes to 0 to a function d for almost every time and locally uniformly with, so what is the function d? We have that d plus is a super solution and d minus is a subsolution. As before, distance super. That is, when flattening does not happen, we have uniqueness in the limit, and our algorithm converges toward the unique solution. Ah, okay. A small note, I won't enter into details, but a small note is that this algorithm makes sense, okay? So under the general assumptions that we have there, you can check that, so if u is a one Lipschitz function, k convolution with u is still a one Lipschitz function. So taking SD of this makes sense. Okay, that's the only part. And from this, you just need the point 2. The point 3 is somehow technical, and the point 4 is to show convergence to something. 5, yeah. So I won't make the computations, but I will tell you that, so examples. Of kappa epsilon. No, maybe I will, no, okay, no. So some examples of kernels that fit in the framework. So the ones associated to. So the first thing, again, is the Euler explicit scheme, which of course I erased. So as before, you can write down what is it, and then you can check that all the assumptions are satisfied, but the positivity of the kernel. In order to require the positivity of the kernel here, you need an extra assumption, which is essentially that also h is less or equal than epsilon squared, morally. But so the theorem is still true. The only thing is that when you are checking assumption 3, naturally you will need that h is smaller or equal than epsilon squared. So okay. So, but something more interesting. So we have also Euler implicit, which would read as follow. Sorry. So Euler implicit kappa epsilon is the kernel associated to the following equation. You are solving this. Okay, so you solve this, you get UK plus 1. If you write everything in Fourier space, you get that this is 1 over 1 plus h delta epsilon Fourier, morally. Okay, so you can check that this pointwise converges to the, I mean, this minus 1 over h converges pointwise to the symbol of the Laplacian. Okay, it's a super easy computation, and this is for most bachelors, I think, not only in Bonn. Maybe also me, I could have done it. But also some other interesting things. So the heat kernel, discrete heat kernel. Namely, you solve dTV equal delta epsilon v with initial condition being u epsilon k. And then you say that u epsilon k plus 1 is equal to v at a time, let's say tau h, okay? So again, a little bit cheating, but here, so even here, when you are defining the kernel or the scheme, you have a time discretization parameter which naturally pops out. And then when you are computing the second moment, so that h that I defined before, it ends up that tau is equal to h. Okay, so you can do the computation, it's quite easy. And also for this one, I mean, here the kappa in Fourier is given essentially by the exponential of t delta epsilon, sorry, h. So again, by a simple limit, you get the convergence. So what's the point? What's the point in 5 minutes? What is the point? Who knows? I have plenty of things to do. So, okay, so. I don't think 5 minutes is much time. So what will I do? Probably not erasing this, maybe. No, yes, I will erase it. Let's go. Okay, so I won't enter, unluckily, into much details about the proof. I must say that the proof, it's quite easy concept. Okay, I will write it down. So proof, idea. So after the Chambol, the paper Bantonan, Max, and Marcello, and if I may say so, also after our paper, it became quite clear that in order to show convergence in this kind of flows towards distributional solutions, you just need two things. The first one is an estimate on balls. You need an estimate on the evolution speed of balls. Just balls, only balls. You need to essentially estimate, say that if you take a ball and you do one step of your algorithm, the evolution law morally is of order h. So it's linear in time. And this in terms gives you compactness in time plus, let's say, curvature bounds. So I will go a little bit quick on that. But why is it so important? So you are working with distance function, uniformly Lipschitz function. So you, for free, have compactness, uniform compactness to answer. So compactness in the locally uniform topology. On the other hand, in time, you don't have anything. So what you need is something which gives you a little bit of compactness in time, and this in turn is given by this kind of lemma. So when you are we are saying that the balls shrink linearly, you get a little bit of uniform continuity in time, at least in all regions which are the form essentially d strictly greater than, I don't know, eta with eta positive. But it's kind of sufficient when you are proving that kind of results. So this is I mean, it's not super technical actually. It's you need to do some tailored development of the modulus on the grid. But here you essentially need to require that h will be bigger or equal than epsilon squared. Because you essentially have a ball, you evolve it, and then you create an order which is over the epsilon squared. So if you want to have it linear in time, you need to require that kind of thing. The second part, of course, is the convergence towards the right equation in the limit. So I will spend, oh wow, two minutes trying to convince you that it's here that the pointwise convergence in Fourier comes into place, and why we need to use distributional solutions in and not viscosity solutions. At the end of the story, the two are the same. So you can show that if you are satisfying that equation in distributional sense, you also satisfy it in the viscosity and vice versa. But the interesting thing is that the convergence, the pointwise convergence in Fourier we require here is too weak, at least for us, to pass to the limit in the viscosity sense there, okay? But not in the distributional sense. So what you do, you take essentially test function eta which is smooth and compactly supported in the region. Okay, let me cheat a bit. The epsilon strictly positive. But okay, valued with positive values, right? And what you do is essentially you want to test your algorithm there, get something in integral form, and pass to the limit. So the first remark is the one that I did before. So since the support of eta is in this region, you can show that essentially your algorithm, let's say 10t plus h, again, by the properties of the distance function, looks as this inequality. Okay? Again, by the same trick that we did before. Okay, so what you do then? You add, subtract, and divide. Okay, so you took your first inequality, you subtract the epsilon t, and you just say, okay, it's a convolution with the delta. You divide by h, and now you see where the Fourier term comes from, right? So if this converges towards the Laplacian in some strong enough sense, you can pass to the limit. Because what you do, you take this, you integrate. Okay. So you integrate this equation. So you integrate eta. So this is a discrete function. So actually you integrate, let's say, from 0 to capital T, then you sum over the whole space with a weight, because this is the discretization of the integral. Everything here will be evaluated at j, there is a multiply by eta j, and you do the same here, tac, sum coefficients, eta. You integrate by parts. So this, by a discrete integration, I mean, Eastern integration by part, you change a variable. You get that this is integral epsilon n sum the discrete time derivative of eta j d epsilon j time t plus h, not t, sorry. Okay, and this term passes to the limit easily. Okay, because you have a locally uniform convergence, and this is compact, whatever. Okay, no problem. So this is going to minus integral double integral dt eta d. Okay, the left-hand side. What about this? So the first thing, you can always do a integration by parts. So you get that this is equal to integral weighted sum of kappa epsilon minus delta over h eta convolution eta times the epsilon t. Okay. So what you wanted to do is you pass in Fourier space, and then this thing essentially converges to the right operator. But this is something which is, of course, Lipschitz, so you are not really able to take a Fourier transform. So the idea here is that first you do this. So essentially what you do is if phi is in L1, then you can show that this is convergent to the right thing. Okay, then you cut off the distance function, you regularize a bit, and you pass to the limit also there. So I'm super cheating here. Essentially, the idea is that, so the true difficult part is that we need here to exploit that eta is smooth and compactly supported, because then the Fourier transform of this is a Schwarz distribution, so you can integrate against the distributional Fourier transform of eta. So that was the catch. And you can see here that you need also to work with distributional solutions, because if you were just viscosity, essentially you had a pointwise equality for eta with this, and just in Fourier space you cannot pass to the limit. So sorry for the overtime, and I thank you all.
Thanks, Daniele, for the nice talk. Do we have a question?
just a curiosity, why you didn't do the anisotropic case because of this Fourier thing?
So no, to be completely honest, so okay, okay. So no, actually, you could have done it if the anisotropic. I mean, if the anisotropy is smooth enough, anisotropy is smooth enough, you could do it. It's not really an issue. Actually, the idea was that since we wanted to somehow model what was going on with the neural network, we didn't really care. And then it brags on and on. It's a year and a half that we have this paper, so we started with the simple case, the isotropic one. So we really wanted to understand what was going on. So yeah, maybe if you want, I didn't say it, but in like the last part of the paper, we also try to investigate what's happening with the real Alencane. So as I said at the start, the neural network is really learning the Alencane equation. In the examples of kernel, there is no Alencane because you cannot really use it. But actually, you can do it by modifying the redistancing operator. It's quite technical, quite painful, so I didn't really have time to do it. But yeah, you can do the anisotropic thing.
Any further question? Okay. Pascal, you have the priority.
Thanks. Yeah, I wanted to ask what kind of the computational complexity of your algorithm is, and maybe to compare it to the other results you presented.
Oh, thanks a lot for the question. So that was another thing I had here, but I didn't say it. So first thing, you can work in Fourier, so it's super fast. You use the FFT on C, in C, you don't have many issues. On the other hand, the distance function, so the redistancing operator, as you have seen, morally, so take for instance D. D is the info over the whole part where the U is negative of something, okay? So it's super expensive. So actually, the issue is that the convolution scheme part is super cheap, the redistancing is super expensive. What we really did after, I mean, okay, so it does work. What you can do is that you can restrict the neighborhood of your interface where you're looking for the distance to compute the redistancing, and this, of course, weights down a lot for the computational part. But if you want to pass to a limit, you need still to let this interface width if you want to go to plus infinity on the scale grid. So morally, what you do is that you have your interface, you keep fixed the width of the interface, but when you're looking at the grid, of course, the number of points here goes to plus infinity. So yeah. So on the other hand, for instance, the MBO scheme, so I didn't say it, but the MBO scheme, you make a diffusion step, which is the hit kernel, and the thresholding is really easy. It's just taking the points where U is less or equal than 1/2. So that thing is pointwise, so it's super fast. But as I was saying before, in the literature, it's well known that doing just that may create pinning if you are not careful enough with the. So I think it's a trade-off. If you, I mean, this is as fast as you want when you are. So we have numerical experiments, and even if this is super narrow, you already get something quite good. So at the end of the day, it's comparable to the like MBO, but you are cheating.
All right, thanks.
Like.
Yeah, thanks for the nice talk. This proof is really nice. So I have a question about the redistancing.
Yeah.
So it's not symmetric, right? Kind of when you change the complement to the complement.
Yes.
So when I remember correctly, if I remember correctly from Selim, he always said he does redistancing because it gives you subgrid accuracy.
Yes, exactly.
But somehow in the estimate, I didn't see it in the proposition where you said kind of it's close to the distance function epsilon. Okay.
So if you want, since in the proposition you have the inequalities are satisfied without error terms, you are not only super accurate, you are exact morally. So which is quite powerful. On the other hand, in order to pass to a limit and essentially say this, so the limit is a distance function, you need a really coarse control on what's going on with the distance, okay? So if you want, the perspective is a little bit changed. I think I mean, you can show that the redistancing we are doing creates at most an error of order epsilon squared. No, morally you do it by when you are doing the estimate of balls, you do something like that. So we are doing an error of order epsilon squared, so a subgrade precision. But the interesting part is that in our algorithm, I mean, in the convergence proof, you do not see this kind of because of the inequalities, you do not see this kind of approximation. That's the main point, because it's well known, for instance, in the MBO, you need a really careful analysis of what's going on. And so maybe to complement a bit also, that's why we cannot use some other really nice kind of redistancing, like the fast marching scheme, economic equation scheme. We do not know what's going on. We do not know even if they are producing a one Lipschitz function in the end, what's the accuracy of, I mean, there is something on the accuracy, but it's too coarse. So yeah, it would be nice, but we don't know how to do it.
Great, yeah, thank you.
Thanks.
Okay, so we thank Daniele for the very nice talk again. Okay, I think we are ready to start again. We hope you enjoyed the cakes. So our next speaker is Salvatore Stuvard from the University of Milan, and he will talk about the epsilon-regularity theorem for Brakke flows near triple junctions. Please.
Okay, thank you very much, Alicia, for the introduction, and I would like to thank all the organizers. So Alicia, Giovanni, Matteo, and Roberta. I said it in alphabetical order by name for the very kind invitation, and it's always a pleasure to be in Pisa, and it's a pleasure to talk about this in Pisa because, of course, I mean, because the proof will be, so the connection with Pisa is that the proof will be based on the blow-up method that was pioneered by Ennio De Giorgi, so this is a nice place to discuss about this. And so what everything I'm going to say is joint work with Yoshito Negawa from, it has changed name, so it's Institute of Science Tokyo now. Okay, so theorem. So you're not gonna find this, so it's still in preparation, and hopefully you will see it appearing on the archive in the next few weeks, but you know how it is. It should have been here, but we didn't make it. So the theorem is as follows. So suppose I'm gonna assume that I have k-dimensional Brakke flow, let's say in a time interval, let's say -4, 0, in a ball. So everything is happening in a parabolic cylinder. And this is k-dimensional in Rn, so this is arbitrary dimension and arbitrary codimension. And the assumption is that this Brakke flow, is weakly close in the L2 sense and in measure to a static unit density cone, which I'm gonna call C, consisting of 3 half planes, which join together along a k-1 dimensional linear subspace of Rn and forming 120 degrees with one another. So what I would call a standard triple junction, k-dimensional triple junction in Rn. Then under certain assumption, which I will detail later, and I will talk extensively about it. And luckily, these assumptions are satisfied virtually in all solutions that I mean, for which all kind of solutions, Brakke flow constructions for which we have existence theorems, and where we expect this kind of singularities. So the theorem is not empty, at least. Then this flow is in a smaller parabolic cylinder, a C1 alpha deformation of the cone. That is, the flow is 3 k-dimensional smooth surfaces, which move in the interior by mean curvature, and they join along, and they join in a C1 alpha fashion along a C1 alpha submanifold, which moves in time, of course, forming angles of 120 degrees with one another. Yeah. Well, yeah, I mean, it's essentially like the theorem of Brakke, if you want, for planes, and it's like the theorem if in the static stationary case is like the theorem of Simon for stationary varifolds. So I mean, I will get there, so to discuss some what was previously known. So the picture is this. This is the cone that I'm talking about. So this is C. in R3. So this is like, I'm gonna call Y1 the standard triple junction in the plane. So the Y cone. And okay, in 3 dimensions, for 2-dimensional surface, this would be the cone that you're looking at. And the assumption is that you have a Brakke flow. I'm gonna come back to what it is. That is L2 close to this guy. And what I want to prove is that then it looks like this, right? If it's L2 close to this guy, then it has to look like this. Then it has to be regular at this cone. It has to look like smooth surfaces that are joining together, forming angles of 120 degrees. I'm very bad at drawing, so but more or less. Okay, so before I get to the goal is to tell you something about the proof of this, but before I get to the proof, I would like to discuss what are these objects, what are the main motivations, why are we interested in this kind of theorem. Okay, so team, thanks, has already talked about Brakke flow. So this is a weak solution to the mean curvature flow. So Brakke, when Brakke introduced it, it was in 1978, I believe, in his PhD thesis. So he was interested in looking at mean curvature flow, not from the point of view of, let's say, differential geometry, as a heat flow of manifolds, let's say. But he was more interested into the kind of applications, maybe to material sciences. And in fact, this is how mean curvature flow was first introduced, and then all the Huisken theory and so on came later. And I think the best is like to describe it in the words of Brakke himself, where he writes in the introduction to the thesis that he's interested in physical systems which move by mean curvature. An example is the motion of grain boundaries in an annealing pure metal. So this is like a picture of what zinc would look like under a microscope. You would see this kind of grains, and you may assume that these grains move when you heat it up and then you let it cool down. Then these grains will rearrange in such a way that they move according to potential energy, which is stored in the interfaces and is proportional to the area of the interfaces. So it's a mean curvature flow. And what he writes is, the question is, what do we mean by surface? We don't want to restrict ourselves to manifolds. Firstly, because a manifold may evolve singularities, and secondly, because systems like grain boundaries, like this, are most interesting when they are not manifolds. And so for surfaces, we shall take a certain class of Radon measures known as varifolds. And I would like to emphasize that in these pictures, you see a lot of triple junctions, right? So that's, in a way, kind of natural that we are interested in describing the flow near these kind of singularities. Okay, Tim already introduced this. So what's a Brakke flow now? I have to describe the equation V equals H into a variable setting. And the idea of Brakke is that the information, if you want the information about the normal velocity of a flow is encoded into this guy, so into the rate of changes of integrals along a flow of test functions, of arbitrary test functions. The idea is that if you know if you know something about this guy for every test function, then you know how the gamma t is moving, right? And this is now assume that gamma t is a smooth flow that moves with any velocity, with velocity v, and then you do this is a simple calculation. I don't know if it's bachelor, but yeah, more or less. And you get this guy, right? So v is the normal velocity of the flow, and this is the kind of quantities, and h is the mean curvature, right? So you have a transport terms that comes from the fact that you're flowing with velocity v, and then this comes from the change of area, right? Along the evolution. And more in general, you can allow for test functions which also depend on time, and then this other term will pop up. Okay, now this in particular, any smooth mean curvature flow on a time interval will satisfy this identity, right? Where in place of v, I've placed h itself. And now it turns out that it makes sense to write all the terms that are here in the sense of varifolds, and I will just do this replacement. So instead of k-dimensional Hausdorff measure restricted to a smooth manifold, I will use the k-dimensional Hausdorff measure restricted to some rectifiable sets, possibly with some multiplicity functions. I don't really have to explain to you guys all of this, you know, maybe better than me, what this looks, what this means. And H here will have to be understood as the approximate mean curvature vector for these varifolds. And this makes sense as long as, well, I mean, you have to make some assumptions. Of course, you have to make assumptions that at least for almost every time, these varifolds V, you know, have bounded first variation, and the first variation does not have singular part, it only has absolutely continuous part. And this H vector is in L2 of space-time, because you have to make sense of this H dotted with H here, right? So as long as you have these assumptions, then this works. There's a caveat though, in that we may not want to require the identity to be satisfied for the weak flows. And there's a reason for that. And the reason is that, okay, smooth flows are going to satisfy the identity. But now you want to, you know, you want to consider weak solutions, and you want to hope that the class of weak solutions that they are considering is large enough that it contains limits of smooth solutions. Now, limits are going to be intended in the sense of varifolds, right? And there's an ugly term here, right? Under varifolds convergence, the integral of h squared is only lower semi-continuous. Here there is a minus sign, so this term is going to be only upper semi-continuous with respect to varifold convergence. So the only thing that makes sense to require in order to have a large enough class in the limit is that the inequality is satisfied. And then, of course, I mean, you have to require a sign on the test functions. What is interesting, and I'm not going to go into that, but what is interesting and really nice is that, in fact, in the smooth setting, so if here in the smooth setting with a smooth velocity field, you only know the inequality, then actually the equality is satisfied. So the inequality is completely characterizing smooth flows. Okay, so this is what we're going to call Brakke's inequality. And okay, as Tim already anticipated, there's a problem in requiring this, in that there is a fundamental drawback in studying Brakke flows, namely that Brakke flows allow what I would call sudden vanishing or possibly catastrophic sudden vanishing of solution. Namely, if you have a Brakke flow, then you can choose your favorite time in the future and decide to put the flow identical equal to 0 after that, and this is still Brakke flow. And this is horrible, of course. So in practice, when I look at Brakke flows, I always want to consider Brakke flows that, together with being Brakke flows, they also satisfy some additional conditions, which guarantee me some sort of, okay, some continuity in time of maybe not the measure, but something. Okay, so I will be more precise later on this. But for the regularity part, what is for me, you know, remarkable is that for regularity, you really just need Brakke's inequality. So maybe for existence, you want to prove existence theorems with Brakke plus something else, but for regularity, Brakke is enough. Okay? So I'm not going to assume anything else. Well, I'm going to assume something else, but okay, let me go to the assumptions. All right. So these are the assumptions of the theorem. I'm going to put them more into I'm going to give a name to the assumptions, A1, A2, A3, up to A5. And then there will be the red assumption in the statement, which is going to be A6. Okay, so assumption A1 is that, I mean, all of these are all reasonables. So you have a flow in B2, in Rn, k-dimensional. For almost every t, this guy is an integral varifold. I'm going to assume locally bounded masses uniformly in time. So I'm going to assume that you have this bound with some constant E1. Now, for Brakke flows, this can be proved. But the truth is that the theorem, I mean, I was stating a subset of the theorem. In fact, I mean, the theorem that we're going to prove is not going to be for Brakke flows, it's going to be for something more than Brakke flows. I mean, I will allow also possibly some perturbation to the velocity field. And in that case, I mean, this has to be an assumption. But for Brakke, this is for free. This is obtained for free. Then I will assume that you have a mean curvature. for almost every time. That is L2 in space-time with respect to the mass. This is reasonable to make sense of this. And then I'm going to assume Brakke's inequality. And this is the Brakke flow that I'm going to consider. And here's where, in fact, I can assume more. In fact, I can assume that the V's satisfy velocity equals to h plus something else, some possible forcing term. Now, this forcing term is given, okay? Is an ambient vector field that is given, and the only assumption that I have to make is that it's integrable enough, okay? I will come back in a second to this. First, let me tell you why I want to consider this. The reason why I want to consider this really is that this allows me to do Brakke flows in Riemannian manifolds, right? Because if I want to do a Brakke flow in a Riemannian manifold, I will take my Riemannian manifold, embed it in Rn with Nash theorem, and then do, you know, Brakke flows in this Rn large N, constraint to live in the manifold, and then the curvature, the mean curvature of the embedding of the manifold inside the larger space will appear as an L infinity forcing term here. So it will enter in this sort of business. I need it for all. I'm gonna assume it for all. Yeah, but it makes sense. It's an upper density. I mean, I just want to say that the upper density is bounded above by something, by whatever, by 100 millions. Okay. Integrable enough means this, as I said, and notice that you know, if you didn't have time, right? So P is the exponent for space integrability, and Q is the exponent for time integrability. If you didn't have time, this condition is the condition that the mean curvature is in LP for P larger than the dimension of the manifold, which is the classical condition for under which you prove Allard's regularity theorem. When I add time, I have to put here a similar condition with the exponent for time integrability, and dimension of time in parabolic problems is 2. Okay, so that's why this exponent appears. And finally, I'm going to assume, and this is really for free, that this is just useful, that the flow is left continuous function of time as a radon measure in B2. And why this is for free? Yeah. Oh, U is an ambient vector field. It's something that is given. So say that you want to flow with velocity, mean curvature plus some vector field that is transporting. Yeah, you remember this is where you would put the V, the velocity field for the flow. Yeah. And the reason why A5 is for free is that because of Brakke's inequality, you can prove that for sufficiently smooth functions, for C2 functions, then the function of time that measures this phi minus possibly some constant which depends on the second derivative of phi times t is monotone non-increasing. Right? For mean curvature flow, right, you would say the measure, right, is decreasing along the flow. Here is not a mean curvature flow. I mean, it's a perturbed mean curvature flow. So if I help this a little bit, right, then I will get a monotone function. And if this is a monotone function, then this guy has a countable set of discontinuities, right? As most. Say it again. Even for mean curvature flow, you have to do that. You're right. You're totally right. You're absolutely right, because you're measuring the you don't have one here. You're totally right. And once you know this, then it means that to satisfy A5, you just have to do a replacement on at most a countable set of singularities, and so it's a replacement that you can do, and that you can assume it has been done, and it doesn't destroy all the other assumptions. Okay. So this is what I'm going to consider, and now let me this is the object that's flowing. Now let me tell you why I want to consider triple junctions. Okay, besides the picture that I showed you before from material science, but where's the mathematics for the triple junction? So in general, and this is something that Teresa has already discussed on Monday, blow-ups or parabolic blow-ups for the mean curvature flow. Right? So in general, in geometric analysis, when you have a problem in geometric analysis, you may want to study the local behavior of solutions by blowing up at some points. And typically to do that, also Alessandra has told us that you really like to have monotonicity formulas. And as Teresa told us, in the business of mean curvature flow, you have a monotonicity formula, which is Huysken's monotonicity formula, which is this one. So what is monotone and is decreasing or non-increasing is the integral of backwards heat kernel, right? So in general, if you fix a point, well, this is written for, let's say, Brakke flows with bounded support, but let's say it is like this. Otherwise, a little perturbation of this. That is true. So for any fixed point in space-time, you can consider this backwards heat kernel, integrate it, and you find that this integral is monotone in time. And this allows you to take parabolic blow-ups. Right? You see, I'm fixing a point in space-time, x naught, t naught, and I am basically translating of t naught in time and x naught in space, and I'm dilating parabolically, right, so that time scales like the square of space. And if I take this parabolic blow-up, then as a consequence of Huysken's monotonicity formula, I know, it's a theorem, that whenever I choose a sequence of dilations which goes to 0, there's a subsequence so that the corresponding Brakke flows converge to a Brakke flow in the limit, which is self-similar. And self-similar means that it satisfies the identity here. And if it satisfies, so this quantity, it has a constant. And if this quantity is constant, then this quantity must be 0. Namely, it's going to satisfy this equation, which is the equation of self-similar solutions to Brakke, or shrinkers, as they're called. In fact, I will not strictly, I mean, they're generally called shrinkers, but there are not just shrinkers here. Among possible blow-ups, possible solutions to this, there are the solutions which are static in time. And if they're static, so namely they're independent of the s variable. If they're static in time, then you see from this equation that they have to be stationary cones. Stationary cones that are just static in time. A classical example of these static solutions or static blow-ups is exactly what happens at regular points. So if you have a mean curvature flow and you have a regular point, that it means that in a parabolic neighborhood of that point, if you have Brakke flow and you have a regular point, it means that in the neighborhood of that point, the solution is a smooth mean curvature flow. And if you do this to a smooth mean curvature flow, then what you see in the limit, as a unique limit, these limits are not generally unique, they depend on the sequence, but in that case, for regular points, what you see in the unique limit is a static plane, right? It's a plane that remains constant in time. Now, it is a theorem, regularity theorem due to Brakke originally, and then that has been improved in certain directions by others, and I will mention Kasai and Tonegawa, Tonegawa and myself, and also a different proof of De Filippis, Gasparetto, and Schulze, that for unit density flows, then the converse is actually true. Namely, and this is what I call Brakke's local regularity theorem, that a flow that is L2 close in a parabolic cylinder to a static plane of multiplicity 1, then it's a C1 alpha graph over that plane in a smaller parabolic cylinder. And this theorem is quantitative in the sense that it comes with estimates where you can estimate the C1 alpha norms of the functions that parameterize the flow with the L2 norm, with the L2 distance from the plane itself. Okay, so we have understood that planes, points where you blow up a static plane are fine, they're regular points. And then, it's reasonable to understand what's coming next. So how do all the others, if you don't blow up a plane, then you cannot be a regular point, right? You must be singular, but it's it's a natural question. Okay, so if I'm blowing up a singular cone, singular static cone, then how does the flow look like? How does the flow look like around it? And well, for most points, the stratification theorem, if you're familiar with stratifications, tells you that most singular points have blow-ups which are static, so time independent, and have a lot of symmetries. Okay, so particularly the first singular stratum that you find, the largest singular stratum that you find, is a stratum of points which admit static blow-ups with dimension of the surface -1 of symmetries. Okay, namely the cones that are being blown up, static cones, are one-dimensional stationary cones in R2 multiplied by a spine of dimension k-1. So the kind of cones that, and of course, since stationary cones in R2 are just union of half lines, right? This is the simplest possible configuration that you may find. Okay, the one with lowest density, the density being 3/2. Okay, so that more or less justifies the reason why we want to understand how the flow looks like around, and I will now make the drawing of this triple junction, right? So these are 120 degrees, and then there is this guy here, 120 degrees. So for me, this guy will be intended as Rk-1, and this is multiplied by the one-dimensional cone, Y cone that is here, right? And I will always refer to this subset, to this subspace, as the spine of the cone. Okay, so when I say the spine of the cone, I just mean this guy. Any questions so far about what the setting looks like? Okay. Oh, this is the blob. Exactly, this is the blob. So I want to study the flow at points which blow up something like this. Now, the theorem will not be like something like if at a point you have a blow up that looks like this. It will be an epsilon-regularity theorem which tells you if by some reason you know that you have a flow that is weakly close to something like this, then it's a deformation of the cone. Whether it's because of a blow up or because of other reasons that you know it, it's always the case. Okay, so being close to a cone. So that's C, that guy there. And now I want to consider the class of flows that are epsilon close to this cone. What does it mean to be epsilon close to the cone? Okay, for simplicity, let's say that we are in codimension 1. So K is the dimension of the surfaces. K+1 is the dimension of the ambient space. K-1 is the dimension of the spine of the cone. And the Y1 is in R2. And from now on, allow me to be inconsistent with my own notation. So far I was denoting points with points in the ambient space with little x. And so from now on, I will denote them with capital X. Because I will want to distinguish the coordinate along the spine, and this is going to be y, and the coordinate along the orthogonal complement to the spine, which is going to be x. So this is going to be x, y. And little x is in R2, y is in Rk-1. Okay? And in particular, the modulus of little x is the distance of the point capital X from the spine of the cone. Right? Okay, so what does it mean to be weakly close to that cone? It means the following. It means that the L2 distance from the cone is smaller than epsilon. Okay, so this is, and also the LP LQ norm of this perturbation ambient vector field is smaller than epsilon. It also means that you're close to the cone. In mass. Namely, that you don't have a multiplicity 2 cone. So this assumption allows you to say, he's telling you that you don't have a double copy of the cone in the blow-up, right? I'm assuming this, notice that I'm assuming this only close to the initial time of the flow, and this is enough to conclude that this is still true for later times, always because the mass is almost decreasing, right, along the flow. So if this is true at the beginning, it's true forever. And then I have to assume something which tells me that, well, until time 0, so the flow is from time -4 to time 0. So 0 is the end time of the flow. I need to tell you that the flow has not disappeared before the end time. I mean, that can happen, right? Brakke flows can disappear. I will assume something which is reasonable for the end time. Namely, I will assume that at the end time, that I'm at the end of the interval of time that I'm considering, here, and here, there is something of the flow. Okay? So there is some measure here, some measure here, and some measure here. Okay, and this is in better terms, I mean more rigorous terms, the theorem that I showed it in the introduction. There is an epsilon 0, which depends only on the numbers that you put in, with the property that if you have a flow which satisfies the 5 assumptions before, and the assumption A6, which has not appeared yet. Like, what are you putting under the carpet here? And that is epsilon close to the cone, for epsilon less than is epsilon 0, then in a smaller parabolic cylinder, you are C1 alpha, C1 zeta. Zeta was this exponent, the formation of the cone. Okay, so I must really tell you what A6 is, right? Okay, so what is A6? A6 is this. So we need to assume the following. In order to prove this theorem, we need to assume the following. And to be honest, we don't know if it's technical assumption or if it's really that without this, you can build solutions which do not satisfy the regularity theorem at triple junctions. We really don't know that. And I will try to explain you. So the idea is the following. So take your cone. You have your flow here, right? At each time, or almost every time, fix a y on the spine of the cone and slice your picture with a plane that is orthogonal to the spine of the cone. Right now, this is a 2-dimensional plane, and this is for almost every t and almost every y. This is cutting the flow, the cone, and the flow in a plane, right? And everything becomes a 1-dimensional picture. Okay, so it becomes exactly this 1-dimensional picture. And I know that for almost every t and almost every y, the slice of the rectifiable set which is supporting the flow at mt and at y is a 1-dimensional rectifiable set. Call it mty. And now you are in this picture here. Take also any point, and you will see when I go to the proof, you will see why I have to take these points that are a little bit far away. Take any point in this red disk and consider, take any point that is more or less close to the origin and consider this red disk around it. So the assumption is the following, that if I call delta the distance between this curve and the cone at scale a half, let's say, then in this disk, in this red disk, the flow has length larger than the length of the triple junction minus a quadratic minus delta squared. what is this? This is essentially, so this is, this I'm comparing length of the curve and length of the triple junction. So for reasonable solutions, such as the one that I'm drawing here, right? If you want a posteriori, if the theorem was true, then this difference would be a second order, right? Is an energy estimate. If you want, you're taking the difference between the two lengths, so the length of the flow and the length of the linearization of the flow. And now the difference should be quadratic in the displacement of the flow from the cone, right? So I'm assuming that this holds true, and this holds true also for these integrals. Okay, if you see it like this, then it really doesn't tell you anything. So let me show you an example of a flow where this does not happen. This is what I don't want. So it's a soft argument to say that if I'm, so because I'm close, so this is like I'm almost entering the proof of the theorem, but because I'm close to the cone, if I cut a tubular neighborhood of the spine of the cone, then away from the tubular neighborhood of the spine of the cone, I will be close to these three planes. And I know that a Brakke flow that is close to a plane is a graph over the plane. So I will know that far away, I start being a nice graph here, a nice graph here, and a nice graph here, right? I have no idea what's happening inside, okay, when I go into a small tubular neighborhood of the spine. Now, the thing is that it's a soft argument to prove that under these assumptions, there must always be a triple junction point inside this red disk. But what the flow could be doing is to enter here, create a triple junction point, but attached to this triple junction point, it does a small loop, comes back, and instead this other guy goes, undisturbed away, right? And this shouldn't happen, right? If you want it to be a perturbation of the cone. So here, this is when this happens, what you see is that the flow has much less mass than the triple junction. Okay, so this is what I don't want to happen. Now the question is, of course, can a Brakke flow that is L2 close to a triple junction do that at many times and many points? The answer is, I don't know. For a general Brakke flow, I don't know. Ideally, my idea, what I have in mind is that if at many times and many points it creates holes like this, then these holes should expand under Brakke flows. And then at large scale, you should see that you're far away from the cone. But here curvatures are just in L2, and it's just difficult to control this kind of behavior. But, so it's like, why are you assuming it? I'm assuming it because in all solutions for which I have existence theorems, and where I expect this kind of singularities, this assumption is satisfied automatically. Okay, so this happens in codimension 1 for what Yoshinai and Kim and Tonegawa call canonical multiphase Brakke flows. So these are Brakke flows in the context of grain boundaries, right? Codimension 1. In 2 words, let me tell you that these are flows where not only you have, they are multiphase flows, where not only you have a flow of surfaces, but you have at the same time flow of sets of finite perimeter, right, which move in time so that their reduced boundary moves by mean curvature, if you want. And now if you are in this situation, if you have a flow that has this additional structure, by the way, this is a kind of solution which does not have that sudden disappearance, so these are solutions that we like. They're kind of what also Tim referred to as BV solutions. In a way, they are Brakke and BV solutions. Now, if you have this structure of sets of finite perimeter, then, well, you're arriving here as graphs, as 3 graphs. So you can say for sure that outside here you have 3 faces, 3 sets of finite perimeter that are wetting the sphere. And now inside you have no idea what the hell is going on, right? There could be many other faces, but what you know is that the length of what is coming in is at least the length of the perimeter cluster minimizer. And that satisfies that assumption. Same is if you want to work in higher codimension. And in higher codimension, well, honestly, the only thing that I know how to produce existence theorems for Brakke flow is to use Hillman-Enz elliptic regularization scheme. But if you want triple junctions, then you should do currents modulo 3. No worries if you don't know what they are, but if we can prove that if you do the elliptic regularization scheme using currents modulo 3, as Hillman and Schulze and White do, then that assumption there is satisfied. Okay, so if you give me other solutions that you have constructed in other ways, I don't know. But then maybe I don't even know if it can suddenly disappear. That, you know, I mean, maybe we just don't want to consider that, right? But this is my personal idea, and then everybody has his own. Okay. So let me tell you what was known. Okay, in the context of Brakke flows, a few years ago in 2016, Yoshito Negawa and Eshan Vikramasekara proved this theorem for curves in the plane. So one-dimensional in the plane. And why they could do it? Why is one-dimensional in the plane is easier? Because you know the energy space for Brakke flows is mean curvature in L2, and 2 happens to be bigger than 1. So 2 bigger than the dimension. There you know that at almost every time you have nice varifolds, and then they're exploiting a lot this. And then a few years later, well, in fact, I mean, these are just publication years, but these 2 papers are essentially contemporary. Felix Schulze and Brian White proved regularity and compactness theorem for some special classes of Brakke flows in arbitrary dimension and codimension near triple junctions. What do I mean with regularity and compactness? They prove theorems like if I have a sequence of these special classes of Brakke flows which converge to a triple junction, then the convergence is in C1 alpha. But they are assuming the structure a priori, and the structure is each surface in the flow is a finite union of smooth embeddings of convex polytopes which meet along edges in triples with 120 degrees. So they're assuming the structure a priori, and they're proving that the convergence is nice. Okay. Instead here, I want to actually show that the structure is that one. So more influential for us is what was done in the stationary context, so the time-independent context. And this was a theorem. I'm really advertising this paper. I mean, it's a beautiful one, and you know, if you like regularity, then you probably have already read it, or you should read it. Here he proved, Leon proved, among other things, that the same theorem as I have stated it now holds in arbitrary dimension and codimension for stationary varifolds which are close to triple junctions. So it's the static case of what we're doing here. We are doing the parabolic version of it. Okay. So let me tell you the proof. I have maybe some 10, 15, I don't know, how much time do you have? 10 minutes. Okay. So in 10 minutes, I will try to tell you what the proof looks like. Okay, of this theorem. So there's a key point. And the key is to prove an excess decay theorem, right? Okay, so this is a theorem that tells you the following. There are a threshold epsilon star, a constancy star, and a scale theta star with the following property, that if you have a forced Brakke flow that is, oh, here there's a C missing, that is epsilon star close to a C cone at scale 1, at parabolic scale 1, then you can find a new cone which is obtained by translating and rotating the whole cone of quantities that are bounded in terms of the L2 norm, of this L2 excess, that is my control parameter that I'm using, so that with respect to this new cone, the excess has decayed. Namely, compared to the excess at scale 1 from the previous cone, the excess at scale theta star with respect to the new cone is much smaller. So in a picture, this is what this theorem looks like. I have a flow, a blue flow, that is close, mu close, to the black cone. Now what I'm at scale 1, so this is the scale 1. What I'm telling you, look, in fact, I can prove you that if I go to a smaller scale, in fact, this blue flow is actually much closer to another cone that I have to find. Okay, so this is the. So now, if you're, if you have done, if you've studied, for example, Allard's theorem, then you will know that this triggers everything, right? That it's essentially the same as Allard. In Allard, you're close to a plane and you find a tilted plane with respect to which the excess decay holds, right? So in this case, instead of tilting the plane, we are rotating the cone, okay? And now the point is, how do I prove something like this? Okay, so U is gonna be equal to 0. So I'm just gonna do Brakke. I'm gonna do mean curvature flow, really. And the proof is via blow-up method. So suppose that it's not true. So if it's not true, then I have a sequence of thresholds epsilon m which goes to 0, and I have sequences of Brakke flows, Vm, which are epsilon m closer and closer, right, to this cone, so that the decay estimate always fails with respect to any possibly translated and rotated cone. And then I want to reach a contradiction. I want to say that from this sequence, I want to generate a cone with respect to which actually decay holds. Okay, how do I do that? Well, first is what I've already told you. For large m, right, the flow is mu m close at scale 1 to the cone C. So if I cut away a tubular neighborhood of the spine of the cone, right, here, if I stay away from here, because I'm close to the cone, away from this tube here, I must be close to either this plane or this plane or this plane. And now, if I am, let's say, sufficiently far away, the hypothesis of the Brakke's regularity theorem kick in. And I have actually nice C1 alpha, C1 zeta graphs coming from here, here, and here, right? Now, this picture stops at some point. When does it stop? The stop is an interplay between, so if you're here, right, then you can rescale up to, how distant you are from the spine, right? Your excess will pay this rescaling, right? So all the estimates will pay the distance from the spine, right? So the estimates degenerate with the distance from the spine. The picture breaks at a certain distance from here, which you can calculate, is of course is of this order. So at this order, the excess is not smaller than epsilon Brakke anymore, and you cannot apply the regularity theorem anymore. Outside of this region, the flow is a C1 zeta graph of a function over some domain of the cone. So this is the picture that you have. You're starting with a nice graph, nice graph, nice graph, and the big red disk where you have no idea what's going on, right? Because you can't apply the regularity of Brakke. Still, and this, of course, the distance here is mu m to some power. Now, this mu m is going to 0, so this picture is just all going to 0. Everything is just converging to the cone, right? So this disk is shrinking. These functions are converging to 0. Okay, so that limit is useless. Which limit I'm gonna take? I'm gonna take a limit of renormalized functions. I take my functions, I divide by the excess, and because I have, estimates, because I had C1 alpha estimates, which were paying the distance from the cone, but okay, these functions converge to a limit, which I'm going to call f tilde, and the convergence is C1 locally away from the spine. So if I stay away from the spine, which in this picture is just this point, if I stay away from 0, if I'm a little bit inside, then here the convergence is nice and C1 alpha. But of course, I have no idea of what the convergence is looking like up to the spine, right? And you understand that if I don't know anything about how the convergence is going to the spine, then I cannot say anything of how this flow is behaving. So this is kind of soft until now, and this is where the hard estimates come into play. So you need to prove some kind of non-concentration estimates for the L2 norm, for the L2 distance from the cone up to the spine. So this will allow you to prove, if you have non-concentration estimates, it will allow you to prove that the convergence may not be C1 alpha up to the spine, but is strong in L2 to the limit function. And also, it may allow you probably to say something like, okay, so these functions, I mean the limit functions, what are they satisfying? Well, you understand that these are parameterizing a mean curvature flow. So the limit function here should satisfy the linearization of the mean curvature flow, which is going to be the heat equation. The heat equation on this line, on this plane, on this plane, and on this plane. Now, in mind, I have that I want to use decay properties for the solutions of the heat equation. But if I have 3 random solutions of the heat equation, then I don't know how they talk to one another, right? And I cannot say that they decay towards anything. So I need to know how these solutions connect at the spine to say that I have some decay. And this is exactly what you do. So you want to essentially prove that you have compatibility condition besides the equation, besides being caloric, caloric, and caloric. You want to say that at the spine they do something, they have some compatibility in such a way that you can still say that they decay quadratically with respect to their linear part. And maybe you want to compute that linear part and say that the linear part generates something which produces a cone with respect to which you have decay. Okay? And so very quickly, how you do this. The first information is soft, and this is what I was telling you before. This is a consequence of stratification, is that every time you go in, you always find a triple junction point inside. But what is hard to prove is that at these triple junction points, you have estimates of this kind. These are the non-concentration estimates that I'm talking about. They're basically telling you, so this, okay, so what are these guys? These are the functions that are parameterizing the graphs, and these are the locations of these triple junction points, okay? And I don't want to really enter what this means, but it essentially means that that you gain some positive power at the denominator for t going to any time where you find the triple junction. That will essentially tell you that I mean the consequence of this will be, okay, there will be 2 consequences of this. Wait, let me tell you first what the consequences are. The first consequence is that the excess does not concentrate along the spine. You remember that this was the scale where all your estimates were breaking down. And this is telling you that the excess inside the red region is very small with respect to the total amount of excess. It's a small fraction of the excess. This is a positive parameter which you can take as you want. Maybe you want to take it less than a half so that this is still positive. Okay? And this implies that you have strong L2 convergence of this rescale map to their limit. And also, it tells you that if you also renormalize the locations of the triple junctions, then the 3 branches that are the 3 graphs that are coming from either planes actually have trace at the spine given by the orthogonal projection of these locations of triple junction. This is an equation which is telling you that the 3 branches are talking to one another. Okay? And in fact, with some more work, that you have an estimate of this kind. So you can calculate the linear part of the solutions of the heat equation. So again, you have heat solutions, and here you're basically estimating heat minus the linearization of these functions in terms of the L2 norm. So this is a classical estimate for solutions of the heat equation. Once you know that you can do it for these three functions that are talking to one another. And let's look how the linearization looks like. The linearization looks like some you have to imagine that these are functions on the these are graph on the three planes. So that's why there are these orthogonal projections, because you're projecting everything onto the orthogonal of the planes. You have to look, but what you're seeing here is some vector which is telling you how to translate the cone. Then you have some linear function of the distance from the spine with vectors v1, v2, and v3, which are summing to 0. So this part is telling you how the one-dimensional triple junction is rotating. And then you have another piece, which is a linear function of the spine into the orthogonal of the spine. This is a tilt of the spine, okay? So these three terms are telling you translation, rotation of the y, and tilt of the spine of the cone. They're telling you exactly where you have to shoot to find decay, because with respect to this guy, this is decaying quadratically because of heat. And then you compare this decay with the contradiction assumption that you had before, and they don't match for a small scale. And this is what I was telling you. So these terms are telling you how to translate, rotate the 1D junction, and tilt the spine to obtain a new cone with respect to which excess decay holds. Now that you have... Okay, in the proof of this, what is remarkable, I didn't tell you how to prove the non-concentration estimates. And I will essentially not tell you, but what is remarkable is that you can prove them from Brakke's inequality. Just by taking Brakke's inequality and testing it with suitable functions, okay? Many suitable functions, so you have to do and do estimates. And it's in these estimates that you need that bloody assumption A6, because there are some terms that you can estimate only if you have this length estimates over there. In the stationary case, Simon did not need A6. He did not need A6 because there he could cleverly use the monotonicity formula for stationary variables, which allows you to control the difference in area between a flow and its tangent. I've tried a lot with Huisken and I failed. I can't do the same with Huisken's monotonicity formula, essentially because Huisken is intrinsically non-local, right? It has this exponential which takes I didn't manage, but maybe it's possible. I don't know. I went to other monotonicity formulas. There is actually, and I'm advertising this, there is a paper on the Annals of Mathematics from Klaus Ecker with the local monotonicity formula for mean curvature flow, which it seems to me that has been never used for doing regularity stuff. So check it out. If you can do something about it, we will all be maybe happy. Klaus will be happy for sure. Once you have all this decay machinery, then it's essentially, when you have all this machinery in place, then you can iterate. The excess will never stop. You will find a cone with respect to which this excess, the smallness of the excess will never stop. So you will keep on going. That red zone will never be a red zone. It will keep on going inside. And eventually you will have your C1 alpha deformation. Sorry, I went a little bit over time. Thanks.
Sorry for the nice talk. Do we have any question for Salvatore? Okay, one there. Who wants to start? Team Alessandra?
Yeah, thanks for the nice talk. So you already said that your A6 is not so bad. I mean, kind of, I wanted to ask, I mean, it's obviously satisfied in most cases somehow.
Yeah.
Also for your canonical Brakke flow. So maybe it would be nice to have a kind of the simplest, not coming from the construction and not using all your canonical Brakke flow, but kind of just it's basically a topological condition that, I mean, kind of you have the grains. So somehow, is there a minimal condition that you can state there that is not kind of that implies A6, where I can say then it works easily? And then my second question is, can you simplify the proof under this assumption, because kind of that the F's meet somehow? That seems also maybe. I'm just wondering. I mean, it's a beautiful.
Yeah, I
thing,
understand.
but,
Understand.
Try to understand.
I understand. Okay. Maybe I will answer first to the second part of the question.
Okay. Yeah.
Okay, that condition is, I'm not sure. I haven't completely thought about it, but I'm not sure that you can really simplify much, because that is really an energetic. I mean, it's if you want, with respect to non-concentration, it's kind of a soft estimate. So it's like you're just comparing lengths, and you're not really saying that you're meeting. You're just saying that the length is I mean, that the length is at least that one minus the distance at that scale. So, but it could really be doing a lot. It could be doing a lot more inside the region. I mean, I just want to say that I don't have holes, right? So I think that I don't know. Maybe it's possible to simplify, but I don't see how at the moment. The other question is very interesting question. I haven't thought about a minimal assumption. Okay, so let's say I've done a lot of stuff in higher codimension, but I still feel more confident to work in codimension 1. Yeah, in codimension 1, basically it's really telling you that
brains, right?
Exactly, you have sets of finite perimeter structure, and then and that you can compare with the perimeter minimizer. I mean, you know, the perimeter minimizer is always gonna be there, and it's gonna do exactly what you want it to do. So whenever you have that, probably whenever you have kind of BV structure solution,
So
probably your solution, the Georgi type solutions there.
Yeah, I would think so too. Yeah, probably. Yeah.
They would work just fine.
Yeah.
I think they would work.
You need of course, the Brakke kind of.
Sure, you need the Brakke. You need Brakke. You need Brakke's inequality, because otherwise all of these I cannot do it. But yeah, I think that probably something in the setting of what you've done is good enough for this.
And maybe one stupid question.
Yeah.
So I mean, there's always this multiplicity 1, even in the flat.
Yeah.
Well,
I don't know how to do the plane in either multiplicity, so I first have to do the plane, and then I have to do the. Okay, but it's a very serious question, and it deserves a serious answer. You need to do the plane. If you want to do the plane, then I mean, I can tell you that it's sort of. I mean, it may be some sort of work in progress on my side.
Okay.
You gotta do multiple valued functions in the parabolic setting, and you may want to do Almgren, or you may want to do something like that. It may be possible.
Then you have these grim reaper solutions. Kind of, you can have a multiplicity 2 plane that disappears at any time, right?
Yeah,
so
exactly.
This is pretty amazing. But I mean,
exactly. So you really have to. You really have to kill all these kinds of behavior. And I mean, first the plane, and then first the plane, and then But once you have the plane, even if it's multiple. Then sort of you may be thinking of doing something like this, in the sense, I mean, I've done it for mod P currents when I have planes coming in with multiplicities. So I had multiple valued functions outside, and it was coming in. I mean, we did it with Camillo and the other guys. So it may be possible to do it parabolically at this point.
So first of all, thank you very much for this tour de force in regularity theory.
Sorry about that.
No, it was a compliment. It was intended as a compliment. So the question is there some hope that after Y comes the T? Let's say at least codimension one canonical Brakke flow to start from.
You could try, okay, here on the spot, I would tell you it works. Just do Luca, Maria, and it was Luca, Maria, and Nick, right? Proof. But you need to assume.
Well, but the last estimate is going to change. Your phi, your F, your B, or this part, this is surely going to change.
Yeah, this is surely gonna change. But I mean, I'm not saying that it's. But I think that you may try to attack it with the ideas of. In the static case, it was done right by Luca, Maria, and Nick. And the idea is like where you have planes, you go with Allard. Here you would go with Brakke. At the triple junctions, you would go with this theorem, and then you will have to put things to patch things together and get the non-concentration estimates. So of course, you need also they are assuming grain structure if you want there, because the T does not have the no-holes condition inside. So in general, I mean, if you just station. So I would tell you that if you are, let's say, codimension one and grain structure, then probably you can try to adapt that proof. And I don't see why it wouldn't really work. But
okay, thank you. Any other question? Okay, if not, then we thank Salvatore again for the nice talk.